We're going to start, this is section 1.2. This is going to be about functions. Talk about functions, what is a function, what does it do, how do we use it, and we'll have a homework assignment on this as well. So make sure we know how to do this. Make sure we know what we're doing here. Functions, usually things like f of x or g of x. It's supposed to be an or really any letter h of x. Sometimes you have like s of t, or you can have m of w. Really any kind of letter like this, any symbol like this, this is our function notation, right? Why am I messing this up? Functions are written things like this. F of x, g of x, all these kind of things. These are all our functions, right? And so the definition of a function, is, hold on everyone. Come on here. A function is a relationship that, come on now. Oh God, what? No. A relationship that maps an input to an output. A function is simply just something that maps these inputs to outputs. Yeah, s of e, or this would be s of t. I wrote a t here, but it doesn't really matter. The letters are, I mean, they mean something, right? But the letters are kind of arbitrary. Usually we use x, and usually it's f of x is our most common one. But you can have g's or h's or s of t's or whatever other variables you have here. But the definition of a relationship of a function is a relationship that maps some inputs to some output. Now, maps an input to an output. Inputs are things like x or t. Inputs are the input variables. Usually x, sometimes t. T stands for usually for time. Sometimes we use input for time. And those are our inputs. Input to an output. Inputs are things like x or like t, for example. Outputs are usually the y, which in this case is the same thing as the f of x that you put in. X or t, for example. Outputs are the y value, which is the same thing as the f of x. Oh goodness, what's going on here? So give me 1 second, everybody. So those are our inputs and outputs, right? So a function is this relationship. All it does is map inputs to outputs. It shows us if I plug in this number, I'm going to get this number out. Just a simple like relationship. There are a few ways that we represent functions, though. There are 3 main ways to represent a function. Represent a function. Three main ways that we represent a function. First way, most common, is we have some points, right? Points which are x, comma, y. This represents, right, our input, and it's mapping it, right? Whatever that input, it says, well, if we give that x input there, our output is going to be whatever this y is, right? It's like a connection. We're drawing a connection. We're saying that this x goes with this y. This is our connection between these inputs and outputs. So points are one of those things, right? So like I can have a list of points. For example, I can have the points like 1, 2, 3, 4, and 5, 6. And this maps all these inputs, all these x values, 1, 3, and 5, are mapped. 1 is mapped to 2, 3 is mapped to 4, 5 goes to 6. They map us together with inputs and outputs. And you've seen points all the time, right? But thinking about them as a relationship might be new. Thinking about points as something where that x value is an input value. It's like if you're using a vending machine, right? Your input is the dollar bills that you put into the machine, and the output is the soda. It's like an exchange, right? Functions represent this kind of exchange, where you give something and you get something. The giving is the input, that's their x value. The getting is the y. And we have this functional relationship between things. And so points are a way to represent that. Another way we represent that, second way, is we can use a table. Right? We can have x and y, and we can do something like 1, 2, 3, 4, 5, 6, right? This is a really ugly table, but you get the idea. And again, we have our input values mapped to our output values. Another way to represent that, right? Another way to represent that. Inputs mapped to outputs. We use tables as functions all the time. Showing us what connects to what, right? Where they go. And like points and tables, they kind of are, they're the same, they mean the same things, right? And this is what I mean. Again, pre-calculus, the point of this class is having us take a step back to realize the bigger picture of what's happening with these values. Points and tables are all the same. They're representations of this transaction that happens. A third way, sometimes we have this way, is what's doing something called a mapping diagram. And you can map these, like for example, if I have all my inputs, 1, 3, and 5, all together, and all my outputs together, 2, 4, and 6, I can draw a connection. I can say, well, 1 goes to 2, 3 goes to 4, and 5 goes to 6, right? If I input, right, my inputs again are here, and my outputs go here. These kinds of diagrams are another way to show a function's like connection between the points. Drawing this connection between inputs and outputs. Okay. So that's three ways. We have a lot of other ways we represent functions, like we have equations that can represent a function. We have lots of other ways, but these are the main three we're going to be using, talking about, right? Points, tables, and graphs, maps, in other words. A graph is also a way to represent a function. There's lots of other ways. But we have this idea, these two values, inputs and outputs. But mathematicians, they like to use very specific language when talking about values of points, like this idea of functions. We don't want to use the word input and output. Those are boring words. Mathematicians like to have their own fancy words. We got to invent our own words, make our own language. Forget your inputs and outputs. I got to use the fancy words. So the words we use instead of inputs, this is what is called the domain. Inputs are the domain, and output is a range. We have these other words for inputs and outputs. Input is domain, output is range. And that's what we mean when we talk about function. Domain is inputs, and range is outputs. We got to have fancy words. Can't have these normal words in our math. Let me say this. Domain is, I should say, the domain is all the inputs and the range is all the outputs. All the inputs, we call that the domain, and all the outputs are the range. Questions so far? All right. So domain, range, input, output, these functions, these mapping diagrams, all these details here explaining how we talk about functions. However, there are some rules that we have to follow in order to be a function. Rules. Rules. What am I going to say? Rules. So to be a function, you, let me say, in order for a function to follow these rules, in order to be a function, each input must only have one output. So to be a function, each input must only have one output. One unique output. Each input must only have one output to be a function. You may have heard this before, aka as a vertical line test. Vertical line test. We've seen that before, maybe as a vertical line test. And I'll show you what that means. But to be a function, if you have these mapping relationships, right, you have to make sure that each input only has one output. Like, so for example, let me give you an example. Say we have a table. Let's represent a function like a table, x and y. Right? Say I have the number 1 going to -3, 2 going to 6, 5 going to 0, 2 going to 7, and 9 going to 1. Is this a function? Is that a function? Each input has one output, right? So 1 goes to -3, 2 goes to 6, right? So we're looking like it's 1 to 1, pretty okay. Edward says yeah. Anyone else? Any ideas? Remember, each input has to only have one output. Look at our inputs. Anybody see something there? Anybody notice something about our inputs? Look at our inputs. Anybody notice anything? Ah! Sakara, yeah. Edward, 2, 2, 2. Yes, there's 8. 2 happens twice. Yeah, 2 numbers are the same. This, and each one of my inputs, one of my 2's goes to 6, and one of my 2's goes to 7. And that is not allowed, right? I am not allowed to have the same what is this kind? Like a repeated x in my inputs cannot repeat. X Someone had a comment? Yes, it is illegal. Breaking the law, not allowed. X cannot repeat. So this is not a function, no. Not nay. No. Because my inputs repeated themselves, I'm not allowed. This is not a function. Breaking the law. What's another one? Let's do another example. How about like let's map your classes. For example, let's go over here. Example. Another example. Let's say you have period 1, period 2. Let's call this period 3, period 2, period 4. Period 5. Oh, God. I'm just getting messier and messier. Period 5. Is your class list a function? Period 5, period 6, period 7. Is your class list a function? Let's say period 1 you have, what is it? Word period 5, right? No, 2, 4, this is 6. This is, so math. Maybe period 1 you have PE, and maybe like science here. Maybe you have English. Maybe you have history. You have maybe photo, you're taking photo. Maybe period 7 you have, what other class? What's another class? PE, history, English. Maybe you're taking a college class. Sure. And so this is a map, right? This is a map. Period 1 you have PE, 2 science, 3 English, 4 history. Is your class list a function? We've got our domain. We've got our range. Is this a function? People say yes. Yeah, I think this is fine. Because, again, nothing repeats. X does not repeat. All the inputs are unique. All the outputs are unique. So, yes, not a problem. That's a function. One more example. What about something like this? Let's say, oh God, sorry. Let's say we have this. Let's do another map. Map. Here's all my inputs. 1, 2, 3, 4. And let's say like these are people, and let's say what do their names begin with? Some people's name begins with A. Some people's name begins with B. Some people's name begins with C. Right? Well, let's make it even more people. Let's make it even more people. More than just these 4. Let's say there's like 6 people. 1, 2, 3, 4, 5, 6. And we want to map what their name, the first letter of their first name. So person number one, their name starts with, let me do green. Person number 1, their name starts with A. Person number 2's name starts with C. But person number 3's name also starts with A. And person number 4. Person number 5 starts with B. And person number 6 also starts with C. So we've got this kind of crazy map going on here. So this is person. And this is letter person, and this is letter of their name. Letter. Is this a function? Letter of their first name. Is this a function? So we mapped people to names, inputs to outputs. Some people say yes, some people say no. So for the people saying yes, but we have some repeats, right? I mean, 1 and 3 and 4 all go to A. 1 and 3 and 4 all go to A. Why is that okay? Is that okay? Is that allowed? What's your reason? Someone want to chime in? Jesus, the input does not repeat. Yes. That is a good... Let's look at our definition. To be a function, each input must only have one output. Here are our inputs. Do our inputs split themselves apart? No. Each input only has one output. 1 goes to A. The outputs can repeat as many times as they want. We do not care. The outputs can repeat. We could all have like the same letter. They could all be going to A. It doesn't matter. As long as each input only has one output. So very good. This is yes. Each input has one output. Outputs can repeat. We do not care. They could all go to the same thing. Doesn't matter. So as long as our inputs only go one time, right? If I had something like if, for example, this person's first name started with A and B, if person number 1 had like 2 different first name letters, that would not be allowed, right? That would be not a function. But we don't have that. They only have one. So that's fine. Great. Good. So we see this function in different different pictures, different ways to see these functions, right? Sometimes you have numbers, letters, you have maps, you have tables, all these kinds of things. We also have graphs. So most functions, I will say, most functions are, or most equations are functions, right? Most equations. Let's talk about equations. Equations. Most equations are functions. Most equations are functions. So, like, we have things like y equals mx plus b, right? Like y equals 2x minus 1. The graph of this function looks something like this. These are functions. These are the things that are functions. So like any line, any linear equation, gonna be a function, right? It's a function, and we can tell because if we imagine our vertical line test, some of you may have heard about this vertical line test before. The vertical line test, what that test did is imagine like a pencil, straight up and down, and you scan across this line, right? Oh God. Stop it. Scan across the line, scan, 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 scan. And as long as your vertical line only touches one time, then it's okay. As long as your vertical line only touches this graph in one spot, right? We touch only one time here, touch one time here, one time here, one time here, one time here. As long as your line only touches in one spot, you're okay. That's the vertical line test. And that is testing to see if there's two inputs. Vertical line, right? The vertical line is x. If there's more than one, if you touch twice, you're not a function. Most functions are past this vertical line test. Most functions are fine. Let me undo my drawing here. As long as it only touches one time, I don't want to have my... There. So vertical line test, imagine, right? A vertical line scanning across. Scanning across, scan. Only touch one spot. So that's fine. Other functions that we have are our parabola, right? Y equals x squared. Parabolas, also fine. Parabolas are functions, not a problem. Other things like y equals the square root of x. There's an interesting graph. That graph looks like this. Draw this a little better. Kind of goes out like that. That's a function too. Doesn't go like all the way back and forth, but we only have one input for each output. Passes our vertical line test, no problem. Things like things like no, stop it. Things like what? Things like, fine, fine, fine. You don't like it? You don't like it? Fine. Things like y equals the absolute value of x is also a function. Absolute value function is this v. Maybe draw this a little bit better. Absolute value function looks like that. Absolute value, that's okay. Not a problem. Even an equation like y equals 6, our straight line, that's a function. Still passes our vertical line test. Oh, God. Still passes our vertical line test, right? Y equals 6. Also a function. So all of these are fine. In fact, any exponent. Exponential, we also have exponential equations. Like y equals 2 to the power of x. That's a function. Looks like this, exponential equations. Right? Also functions. Most equations that you see, most normal equations are going to be functions. Things that are not functions. What are those? Things that are not functions. Things that do not count. So things that are not functions are equations like things like x equals y squared. This looks like this, a sideways parabola. And that, if we imagine a vertical line test, touches twice. And that's why that's not allowed. Or things like x, stop it. Things like x squared plus y squared equals 1. This graph is of a circle. X squared plus y squared equals 1. Let me draw this a little bit better. X squared plus y squared equals 1. Not a function, because again, that graph looks like a circle, doesn't pass the vertical line test. Or like x equals the absolute value of y. Again, this is our sideways absolute value sign, also not a function. Or even something like x equals 6. X equals 6, vertical line straight up and down, not a function. And so there are some clues that we can use to help guide us to decide if an equation is a function or not. There's some clues we can use. And if we notice, like all the regular equations are fine, but things get a little weird when instead of like a y equals equation, I have this like x equals equation. That's when things get weird. Or this x squared plus y squared, or x equals the absolute value of y, right? When things get like backwards, when things are in reverse, that's when things get weird. And so a good clue is, look at this. We have y squared. If you have a y squared, anywhere in your equation, if y is squared, you're not going to be a function. If you have y in an absolute value, anywhere in your equation, you're not going to be a function. X absolute value, totally fine. Y absolute value, not fine. X is squared, no problem. Y is squared, not going to be a function. So these are little like clues that we can have. In this last one, we only have x, there's no y at all. So no y in your equation at all, that's going to be a problem. If I don't have an x, if I just have a y by itself, that's fine. X by itself, not fine. So we can say y equals 2 to the power of x. Yes, this down here? Yeah, y equals 2 to the power of x. Yeah. Y equals 2 to the power of x. Exponential equation. So a clue we can use is, how do you want to say it? Like, if we have an x squared, not x squared. If you have y squared, if you have an absolute value of y, or if you have no y at all, these things are not a function. So those are our clues. Okay. Questions? Anybody want me to like read something? Mister, what is that squiggle? It's okay? Whoop. So we have some ways we represent functions. We can represent them with tables, with a graph, with points. We can represent them with graphs or equations, and we can recognize. Now we can recognize what things are functions and what are not. Right? Functions are, the rule is you cannot repeat your input. Inputs cannot repeat. The rule is it has to be this vertical line test where you scan, you only have to touch one time. Here we're touching twice. So if you look at a graph, that's not a function. And if it has these x squareds or y squared or absolute value of y or no y at all, these are clues that tell us something is not a function. And so again, what we're doing is we're taking a step back in pre-calculus. We're looking at this bigger picture and seeing these patterns evolve, seeing these connections, and the idea that points and lines and equations and tables all show the same thing. And they're all ways to represent this relationship of input to output. And that's what a function represents. Okay. So let's use these functions. Let's with them. Let's do some like values. Let's find some values of functions. What if we were to like, how do we use functions? Finding values of functions. So for example, let's say we have a function f of x, and let's say this is 3x plus 2 over x minus 5. Here's my function. Some equation, some function, right? F, we use f of x, right? That's just the name we give the function. Right? F is just the function name. Function f. And x, right? X is our input. So if I wanted to say, if I wanted to find f of 1, that means, of course, I'm going to take this 1, take this value 1, and plug it into my x's, right? Plug into my x's. Every x I see, right, gets plugged in, right? Plug in x equals 1. So I do this, I'm going to get 3 times 1 plus 2 over 1 minus 5. So 3 times 1 is 3 plus 2 over negative 4, so 5 over negative 4. There's my answer. And I would say, to write this out correctly, I would say, where'd my pen go? I would say f of 1 equals 5 over negative 4. And that's showing me that with an input of 1, in this function f, with an input of 1, I get an output of negative 5 over 4. Is what that's saying. Right, we've seen this kind of thing before. Finding values, right? You're plugging it. Mr. Mitchell, this is like, it's like I learned this in 7th grade. What are you doing? Okay, good. I'm glad. Let's make it a little harder. Let's make it a little more interesting. Fine, you did this earlier. Let's see what you do if we have this kind of equation. Let's do another example. Let's say f of x is equal to 3. No, let's go 3. Let's say we have f of x is equal to no, same function. Let's use our same function here. Let's not change the function. Instead of finding what happens if I plug in a 1, we're going to plug in, plug in an equation. I want us to find what is f of x squared minus 2. Huh? You can't plug an equation into an equation. Sure you can. Why not? Who's going to stop us? You going to stop us? I don't think so. We'll plug an equation into our equation. Equations all the way down. So I'm going to plug x squared minus 2 into my function. So we're going to take this x squared minus 2. We're going to say, okay, this is equal to 3. And again, take this whole thing. Let me do this in blue. Take this whole thing, x squared minus 2, and we're going to plug it everywhere we see an x. X squared minus 2. So it's 3x squared minus 2 plus 2 over x squared minus 2 minus 5. Everywhere you see an x, you replace it with this x squared minus 2. Same function, same f. Now we're plugging in this more complicated thing. And now we have this bigger equation, and we have to simplify. So I can, for example, distribute the 3. Right? What if I distribute my 3? So let's do, this is going to become 3x squared minus 6 plus 2 over, I don't need to distribute anything here, x squared minus 2 minus 5. So I can combine, right, these two and can combine these two. 3x squared minus 6 plus 2 is minus 4. X squared minus 2 minus 5 is minus 7. And that's a 4. Let me do that better. Minus 4. And this is the answer. So I would say f of x squared minus 2 equals 3x squared minus 4 over x squared minus 7. And so if I plug in an equation, I'm going to get out an equation. Minus 4. Okay. Another example, what if we have g of x? Let me do a different equation. G of x equals x squared plus 1. Oh, I ran out of space here. Okay, and then what if I want to find find g of x minus 2. So that's going to be, I plug in my x minus 2, let me do this in a different color. Everywhere I see x, so here's my x, everywhere I see x, I'm going to plug in x minus 2. So x minus 2, that whole thing then, for example, gets squared plus 1. Again, I have to simplify. So I have to make this x minus 2 squared. Squared means I have 2 of them. X minus 2 times x minus 2 plus 1. Right? Try this a little bit better. X minus 2 plus 1. And then I would have to distribute these, multiply these together, FOIL this stuff together. We would get, I'm running out of space here. So annoying. I would get, oh, if I move this. Come here. Move you. Oh, good. There we go. There we go. I would get x squared minus 2, right? If you foiled this together, minus 2x plus 4 plus 1, which would be x squared minus 4x minus plus 4 plus 1 is plus 5. And that would be my answer here. This would be my answer here. Let's try not to cover up some of the answer. So this is a little bit more advanced ways of using functions, plugging in equations to functions. Right, take your x squared, you have to plug the x squared in. Huh? Say it again. You can't, oh, you can't see the answer. It's too far down. Okay. Let's see. Can I grab it? Okay, let me try to grab this and move this somewhere else. Oops, cancel. Stop you. Whoa. All right. How about now? Is that okay? Up there? Yeah, we're out of time. All right, so there's the answer. I'm going to save this again. Your homework, I will post it on Schoology. It's going to be out of the book. I want you to tell me if things are functions, plug in some of these functions, and try those questions out. It'll be due the next time we meet on Wednesday, so you'll have a week for it. 1 week. Homework on Schoology. Homework on Schoology. But that is it, everybody. I'm going to post these notes for sure, and I made a recording, so we're good. All right, everyone. There's a lot of stuff. I wanted to get through this, though, because I know the next time we meet is going to be in a week from now. So that's it for me. Say goodbye in the chat. Why don't you say goodbye? You are free to go. I'm going to leave this up here for a second, and I will see you all next time. Thanks very much.